So, yesterday I discussed some basics about path integral quantization for quantum mechanics, an example of a very simple system, the particle in one dimension. I realized that, in fact, part of what I explained, you have probably heard it already once in the course by Maite, but so I hope it has not been boring for you, but I think it's good things to see. Important things explained in two different, slightly different point of view. So I think I will stop there for discussing the path integral in quantum mechanics, because I think you have seen already how from path integral you can derive the least action principle, and so how the classical equation of motion came out in a natural way from path integrals, which was one of the great, discovery or application by Feynman of path integrals, the way that the Lagrangian formulation of quantum mechanics. This is a Lagrangian way to derive, formulate quantum mechanics and to derive Lagrangian mechanics out of quantum mechanics in the same way that you derive by correspondence principle Hamiltonian quantum mechanics from, Hamiltonian classical mechanics from Hamiltonian quantum mechanics. So, but if you have any question about that, we can come back to discuss that. Okay. And I'm going to discuss now, to start, so this is the second part of two, about the quantization of free field, quantization free scalar field by path integrals, which in this case is called functional integral. Okay. So the free scalar field is the object that describes the second quantization of the relativistic particles, of the second quantization of the Klein-Gordon field, of the Klein-Gordon equation. So let me first make some reminds about the free field. So, but you have seen that in detail, I think, already in the QFT1 course. So the classical, let's go first, the classical Klein-Gordon field. So that's 2, 1. Okay, so we have first Minkowski spacetime. Since this is a relativistic theory, so the metric is dS squared is minus dt squared plus dx squared. Okay. Or if you prefer, you can write this 4 coordinate as t and x. Okay, and I'm using the East Coast convention for metric with c equal 1. Okay. And on this Minkowski spacetime, there is a field, a classical field, phi of x, which is a real variable. So there is no spin, no charge. Okay. And so at that level, it's a classical field, and we want to quantize a field whose equation of motion are the Klein-Gordon equation. So for this, we use the action. So the action is a functional of field configuration. So I'm using those brackets. And this is integral over time of some Lagrangian. And the Lagrangian itself can be written as an integral of a space of the Lagrangian density. So I have dx. And the Lagrangian density contains a kinetic part, which is 1/2 of dt phi squared, and a potential part, which contains first the spatial derivative. So this is a gradient with respect to x, if you want, squared, and then a local potential term, which is just quadratic, so it's phi squared. Okay, and phi is taken at the given x. So this is a time derivative, spatial derivative, and the purely local potential term. And so this is the Lagrangian density. Okay, and of course, this can be rewritten as in a Lorentz covariant way as dx 1/2 d mu phi minus 1/2 minus, I'm sorry, there's a minus here with this convention of metric, minus 1/2 of m squared phi squared. Okay, and here I assume that my space-time is d-dimensional. So space has dimension d minus 1. So okay. And in this form, it's clear that the action, so this is a volume element in d-dimensional Minkowski space-time. So it is clear in this, with this notation that the action is Lorentz invariant and Poincaré invariant, in fact, and therefore the equation of motion will be Poincaré invariant. And from that, you can derive by the least action principle that the classical equation of motion are the Klein-Gordon equation. Namely, if I am not mistaken with my notation, it's minus delta. Well, delta is minus d over dt plus, so it's minus delta plus m squared phi equals 0. So that's Klein-Gordon. Okay. Okay. So now, of course, I spent some time yesterday in discussing quantum theory at Euclidean space-time for reasons that are related in particular to the fact that we are interested in quantum theory at finite temperature, but also from some more conceptual point of view. So in Euclidean space-time, so it's still d-dimension. Simply now ds squared is d tau squared plus d x squared. So the x is tau x. So Euclidean time is just the first coordinate in my Euclidean space-time. So this is Euclidean space-time, Euclidean time. And we have seen that then the quantum theory will be described in terms of path integral, in terms of an Euclidean action. The Euclidean action. And remember, the Euclidean action is obtained by making the Wick rotation by changing t into minus I tau. So the Euclidean action is SE of phi. So now we have a field phi, which is a function of this in Euclidean space-time, and this is just, in this case, d dx. This is the Euclidean space-time, and then we have 1/2 of d tau phi squared plus 1/2 of d, well, that's a gradient, so it's a vector gradient with respect to x of phi squared plus m squared over 2 phi squared, which can be rewritten as d dx 1/2 d mu phi squared plus m squared over 2 phi squared. And here it's clear that it's Euclidean, so rotation plus translation invariant. So it's Euclidean. Rotation plus translation. Okay. Okay, so that's the basis. And here it's Poincaré. Lorentz plus translation in time and space. Okay.
So,
yes?
What happens with boost?
With?
Boost. Like, if Lorentz, the Poincaré group is rotations, translations, and boost.
Yeah, but that's what I mean by Lorentz. Lorentz transformation are boosts.
Yeah, but when we go to the Euclidean
well, boost becomes just rotations. Well, in fact, it's... So boost becomes rotation involving the first coordinate. Mm-hmm. So boosts then are just part of the rotations. Okay.
So we will have like a no 4 instead. Like a no 4.
Yeah. Yes. So you have OD. And, with the semi-direct product of OD with RD translation. Where here it's O1 D minus 1, semi-direct product of RD. Time translation, or if you prefer, R plus times RD minus 1, time translation and space translation. Okay. 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 And again, here the the classical equation of motion are going to be the Euclidean Klein-Gordon equation. One last remark. What is this parameter m? So here m is just a parameter, but of course, in the Klein-Gordon equation, it's going to be the mass of the particle. So what is m? One last remark. M is a mass of the quanta, so the first quanta of the field. But here it's not clear that this theory, taken at this step, as particles, as quantum particles. We have not quantized it, it's just a field. Okay. So you must be slightly different. So warning, it's not the mass of the field. It's not the mass of the field. And in fact, the concept of mass of the field is not something well defined. It's the mass of the elementary quantum of the field, the particle, the first excitation of the field. That's what I'm saying. Okay. Okay, so now, how do we quantize this? Okay, you have seen in the QFT1 course that what you do by canonical quantization is that you you look at the elementary modes. So you basically diagonalize this, the solution, the classical solution, in terms of Fourier modes, which turns out to be independent, and then you quantize those modes, and then you build out again a full theory and the full Hilbert space of the theory out of that. Well, using the recipe of path integral, it's at first type straightforward, because we have an action, we have a field, so we can just use path integral. So replace the integral over histories by having an integral over field configurations. Okay. So, of course, I will be sketchy here. So, in fact, your space-time, let me draw space and time in this combination. This is a Minkowski space-time. And of course, you are interested in matrix element of the evolution operator. So in principle, you should define an initial time. Let me call it T1, T initial, Tf. I should put some initial condition, some final condition, which will correspond to, and I am interested in computing the quantum amplitudes of field configuration between this initial state and this final state. So I'm interested in computing some in and, well, let's say out at Tf and initial condition at T initial, matrix element of the evolution operator. Okay. So one has to specify in the integral of a field configuration what are the boundary conditions. So I will come back to that a bit later, but we won't treat that in detail. So, but first I just want to say how can we define something which is going to be an integral over field configuration of exponential of I over h bar, the classical action of this field configuration. We want to define this, is that's going to be the analog for fields of what we did yesterday for quantum mechanics. But we have an analogy because if you think about the special case where d equal 1, so d equal 1 means that we have one time, no space. Or rather, space is just a point. Okay. And then these terms disappear. There is this and this. So the action is integral over d time of a time derivative of phi minus m squared over 2 phi squared. So you recognize the action of a classical harmonic oscillator. And phi of t is just the position of the particle. See? So you see there is an important difference between quantum mechanics and quantum field theory. In quantum mechanics, the position is a degree of freedom of the quantum system. So it can be quantized, it can become an operator. In quantum field theory, x is a coordinate. It plays the same role as time because we need Lorentz invariance. So it's not x that must be quantized. It's a field variable. So the field, the classical field will become an operator acting on a big Hilbert space, but space remains a classical concept. has time at that level. It's only when you try to quantize gravity that time and space will become quantum objects. And it's still something very, not completely clarified. There are several proposals to do that, but okay, so phi is going to become a field. Becomes a field operator, a field quantum operator. And I'm going to show how this is defined by function. Okay, so we want to define that. So this is very formal, but let's assume that this makes sense. And of course, this is in Minkowski. In Euclidean framework, what we expect is we have a field configuration. We have a measure which is going to be an Euclidean measure, and we have an exponential of minus 1 over h bar, the Euclidean action of the field. Okay, so that's Minkowski, and that's Minkowski functional integral, and that's a Minkowski Euclidean functional integral. Okay, so this is what is called the functional integral. So of course, in order to define that, you need to be a bit more careful, because in fact it turns out that this subject is full of infinities. So what we have to do to be a bit more precise is to discretize time, and in the derivation, in the construction of the path integral by Feynman and Kak, and what has been, I think, presented by Maite, you see that in order to master what you are doing, you discretize time and you take a continuum limit. Yes?
Is there if we know the measure in Lorentzian spacetime, the measure phi, is there a way to know that the measure in the Euclidean?
Yes, I'm going to discuss that a bit later. Okay. Good question. Yes, I'm just going to explain what is the measure in the case of discretized spacetime. Okay, so we need to discretize time, but also we need, it's convenient, it's not compulsory, but you need to discretize space. Because a field is a function, so it has an infinite number of degrees of freedom. You can vary the value of the field at any point. So we need to discretize time and space in order to make sense of this. And there are many, many recipes to do that, and there are recipes to define that which doesn't use discretization of time and space, but I'm just going to describe this. So the simplest way, is to replace, so how Minkowski or Euclidean spacetime RD by a lattice ZD with a mesh, let's call it, how is it meshed? Epsilon. So I replace my continuous spacetime by a lattice like this, a square lattice. You can think about more complicated lattice or random lattices or something. Okay. And the mesh is going to be, I call it epsilon, and I take the same mesh in the time direction and in the space direction. Of course, you can take a mesh which is different in the time direction and in the space direction, but it's the simplest case. And at first, it makes sense because it's also valid in Euclidean, where time and space play the same role. And of course, when you do that, you replace the continuous Poincaré symmetry of translation and boosts and rotation in continuous space-time by just the symmetry of this hypercubic lattice. So you replace the continuous Poincaré or Euclidean symmetry by a discrete symmetry, a much, much smaller discrete group, infinite group, but still but discrete. So continuous symmetry becomes discrete symmetry. So that's the price we have to pay. And the very important question will be, once we do the quantization of the discrete theory, can we recover a continuum limit where space and time are continuous and where we recover Poincaré symmetry or Euclidean symmetry? Okay. So now, if we discretize space and time, of course, we replace the position, let's call it x, belonging to Rd, by vector x n equal epsilon some vector n. So n is a vector, so n is a point in ZD. So it's an integer coordinate. So if you can write it, n is n0, n1, up to nd, minus 1, this is time, this is space. Okay. So now, if you play, you just have to follow the rule of the game of quantization by path integral, but apply to this system. So first, you have to replace in this action the derivatives by finite difference. So typically you replace d over dx mu of phi of x. So this is a derivative, the partial derivative of the field with respect to the mu coordinates. So x is x1 up to xd, or x0 up to xd minus 1, if you prefer. This is time, this is continuous space. You replace the partial derivative by finite differences. Namely, you have your lattice. Okay? And this is a point here, xn. This is the direction mu. You have an elementary, you have a unit vector e mu. Let us call it, e mu is a unit vector 0, 1, 0, where this is a mu index. Okay, so this is a unit vector. And so you replace phi of x. So you replace, of course, you replace this. So x is by phi of x plus epsilon e mu minus phi of x. So this is the difference between the field here and the field here. But you have to take a finite difference, so you have to normalize by epsilon to divide by the distance between the 2 points. So this is the finite difference you have to use. So that's the finite, that's the derivative of the finite lattice in the direction mu at point x. Okay? So this is the first rule. First rule, rule 1, replace derivative by finite differences. Okay? Now, rule 2, in the action, we have to replace the integral of a space-time by a sum over the point of the lattice. So rule 2 integrals become sums. So integral over d dx becomes sum over the n vectors belonging to zd, so sum over points on the lattice. But then you have to take into account the volume in space-time of an elementary point, which is just epsilon to the power d. That's the volume in the dimensional space-time of an hyper, cubic cell of size epsilon. Remember, epsilon is the size of the sun. This is epsilon, and it's the same in the different direction. Okay. So using these rules, you can obtain a discretized action, S, let's call it S of phi. So these two rules gives a discretized action. Let's call it S epsilon of phi, which is just going to be sum over n to zd. And we have epsilon d. In fact, we have an epsilon, and then we have 1/2 of this derivative sum from mu equals 0 to d minus 1, phi of, so xn is epsilon. Oh, and then we can, of course, say that phi of xn equal epsilon n is just phi of n, where n is a vector in ZD, so that's phi of n plus e mu. Remember, those are vectors minus phi of n divided by epsilon squared. I'm going to use this for in the Euclidean case. Otherwise, you have to add a minus sign in the first direction and a plus sign, well, a plus sign in this direction and the minus sign. So for the Euclidean action, this is going to be this, and then simply plus m squared over 2 phi of n squared. So you see you have an epsilon squared, so the discrete derivative terms contain an epsilon d minus 2, and the mass term contains an epsilon d. So this is a discretized action. Okay. And same, similar for real-time action. Okay. So now in order to define, so this is a classical discretized action. Now in order to define this path integral, we have also to define, to check what is the measure. So I'm not going to justify entirely, but this is an exercise. Rule 3. What is a measure for discretized field? And I'm just going to state the result. In the Euclidean case, so this is rule 3, so just Euclidean case, the Euclidean measure of phi. Well, as for the, for quantum mechanical case, you expect that the measure is just an independent measure for the value of the field at each time and each space points. So it's going to be here a product over all the points on the hypercubic lattice n. And then we are going to have a d phi n, phi of n, and then there is a normalization factor. And this normalization factor turns out to be 2 pi h bar divided by epsilon d minus 2 to the power minus 1/2. Okay. So this is a specific form of the measure. And that's, in fact, that's very analogous to the term you get in quantum mechanics, where I think, otherwise I can explain that in a bit more detail, but I think Maite told that. The action is 2 pi h bar times the interval in time divided by the mass. And here the interval of time, so the delta t in quantum mechanics, the delta t would be epsilon, and the mass term for the field, the mass term from the field is the term which is in front of the derivative of the field. So it's epsilon d minus 1. It turns out, because there is one epsilon here that comes from the time interval, and then there remain epsilon d minus 1 divided by this. So if you play this game, you end up with epsilon d minus 2. Okay.
Sorry, I don't really understand.
Huh?
I don't really understand. Could you explain that factor of epsilon?
Okay. So, well, maybe. Okay. Well, okay. Maybe just let's skip that at that stage. We can discuss that a bit later after that. But just state that this is the result. There is an epsilon d minus 2 that comes out from the. This comes out from the quantum mechanics rules of the game. Okay, now in the Minkowski spacetime case, the measure is slightly different. It just comes from the fact that you have to change one, you make a Wick rotation. So this is also a product of n belonging to z to the power d, d phi of n. And then you get 2 I pi h bar divided by epsilon d minus 2 to the power minus 1/2. So just the difference between the Euclidean measure and the Minkowski measure is that here there is 2 pi h bar and here there is 2 I pi h bar. Okay, so these are this was the first board 1, board 2. Okay, so these are the rules of the game. And now, typically, when you compute such an object like that, when space and time is discretized, this just becomes Gaussian integral. So we can just come out with the rule of Gaussian integration. So, for instance, you can compute an object like that, where if you want to compute an amplitude, so you have your discretized spacetime. Then you are going to take, okay. Here you have some initial time step. Let's say it's 0. Here you have some final time step, which is t, and let's call it well, some big N times epsilon. So that's the number of steps you have. And then how do you define an initial and a final step? So an initial state is going to be the analog of the fact that you fix the position of the particle at the initial time, will be space, well, initial field configuration in space. So we have an initial field configuration phi I of the space variable x, and in our case x is going to be an epsilon times an d minus 1 dimensional vector. Let's call it n space. D minus 1. The final state is going to be a final field configuration of x, where x now, so this is x is epsilon n, the same way. So you fixed phi initial here and phi final here. Okay? And the amplitude, the rule of the game states that amplitudes, you have phi final at t final and phi initial at t initial. It's going to be given by this big integral, where you integrate over all the discretized action. So for instance here, d of phi. So this is discretized. With an exponential of I over h bar. The action is also discretized. So you integrate over all the possible value of the field at all the points of the lattice in between the initial and the final slice, time slice. But you have, of course, as boundary condition, the fact that phi of x, let's say of t initial and x is phi initial of x. So the field is fixed here, and phi at the final time and any position this is phi initial and this is phi final of x. Okay. See? And as long as you have a discrete integral, this is a Gaussian integral, and you can do the calculation. So you may object, yes, you still have, may have an infinite number of points in space, but you can also make space compact by, for instance, taking boundary condition in space, and then everything is fine. So if you have a finite time slice plus periodic space plus discretization, then this is a finite dimensional Gaussian integral. So we are on safe ground. Okay? So in principle, we know how to compute things. We just have to apply the rule of Gaussian integral that you have seen in both in quantum theory and in statistical mechanics. Okay. And we are going to apply this soon. Okay, so now finally, one last remark before going to some explicit calculation. in quantum field theory, one is interested in the expectation value of the observable, so the correlation function or the green function that you have seen in QFT1 are defined as the matrix element between the vacuum state of products of operator. So the question is, how can we define? So let me define by 0 the vacuum state of the quantum field theory we are considering. So the state where there are no particles, no excitation. Okay, so that's the ground state of the theory, the lowest energy state of the theory. And we are interested in computing, for instance, matrix element between the vacuum state of the theory of products of operator. What we are going to do is to compute, for instance, time-ordered products of operator phi at a point x1 and phi at point x2. So those are field operators. This is a time-ordered product. And this is a green function, and that's basically what's called GF x1, x2. And in QFT1, you have seen that this is called the Feynman propagator. So we're interested in computing this kind of things. So the question is, how do we compute by path integral method or functional integral method matrix element of operators between the vacuum, so vacuum to vacuum matrix element? Okay. Out of this kind of things, when you have initial and final state. Well, the rule is exactly the same than for than in quantum mechanics. No, the rule is, how do we compute this? Well, you have to remember the fact that we have a rule in quantum mechanics to compute matrix element of operators in thermal states. So start from the theory at finite temperature. Okay. We know that if we have a theory at finite temperature, let me call this T E. E for temperature. Remember that T is not a time, but T is a temperature. Okay, we know that to a temperature is associated, to a finite temperature, TE, is associated a period tau, which is h bar over Boltzmann constant times the temperature in Euclidean path integral. See, and for instance, the partition function of the system, the partition function, Z, which is a function of the temperature, is just given by a path integral. And in our case, this is going to be E phi exponential minus 1 over h bar, the Euclidean action of phi, but with some specific boundary condition, which is that phi is periodic in the Euclidean time direction with period tau. And the period tau is related to this temperature by this relation. And this is a universal relation. It's completely independent of the quantum system you are considering. Okay. And therefore, what does this mean? It means that in order to compute objects like that, we have to consider a functional integral of a field where field phi of x, phi of, well, Euclidean phi, so it's phi of Euclidean coordinates. So this is phi of tau of, let's say, sigma and hex. Sigma is a coordinate, but where now this is Euclidean time that I'm calling sigma. This is position, space coordinate, x, and simply, instead of summing over field configurations that are fixed initial and final condition, we just have to make this periodic. We identify 0 and tau for h bar over Boltzmann constant times the temperature. Okay? So we just integrate over all field configuration phi of xa function in this thing, but simply we impose that phi here is equal to phi x. So we just impose that phi of 0 and x is phi, or if you prefer, periodic phi of any tau, any sigma, and x is equal to phi of sigma plus tau and x. You see? So, in some sense, our Euclidean spacetime becomes a cylinder. Let me draw it. So instead of having, so we have an Euclidean spacetime which is periodic. So this is space. So you consider an Euclidean spacetime which is not RD, but it's a cylinder is one direction. Okay? Okay. But now, of course, what remains stated is that the partition function is just given by the sum over the eigenstates of H energy eigenstates of the Boltzmann exponential of minus, well, in this case, this is going to be 1 over kBt times the energy of the state I. And therefore, what's happening, and this is the temperature. And similarly, if we are interested in expectation value in a thermal state of some observable A, what you have to compute is the sum of the eigenstate high with the Boltzmann weight exponential minus 1 over kBt E EI times, it's a trace of A, so it's going to be the matrix element I, some observable operator I of I, and this is normalized by Z. The sum of I exponential of minus 1 over kB times the temperature times the energy eigenstate. Okay? And of course, in any system, you have the ground state 0, which has an energy E0, and then you have excited energy with EI, which are larger than E0. And therefore, in order to get the vacuum, the ground state matrix element of A, what do you have to do? You are interested in 0, A, 0. That's very general. That's very simple. You just have to take the limit when the temperature goes to 0. A, T, E. Because when the temperature goes to 0, of course, the system stays in its ground state. It has no energy fluctuations to go to the excited states. Okay, so this is a very general receipt. So in order to compute, but now, in order to compute vacuum to vacuum amplitudes, matrix element, you just have to take the limit T goes to 0. But TE goes to 0. So of course, equivalent to take the limit when the period tau goes to infinity. So this, this cylinder grows larger and larger and larger, and therefore you just have to consider that instead of having a cylinder, you get an infinite Euclidean space RD, just taking care of the growth of the field at infinity. The field should not grow at infinity in order to be compatible within the limit of a field which is periodic. So if we compute, functional integral in Euclidean infinite space-time, we recover vacuum matrix element. So expectation value in the vacuum of observable. Okay, so that's a receipt. That's a receipt for okay. And that's not specific to the free field. We expect that is going to be true for any theory, any quantum theory, either quantum mechanics or relativistic quantum field theory. Okay. Okay, so now I think I have everything ready for now going to the first application, which is not here. This was 2, this was 3, this is 4. And now let's go to an important application. Compute the 2-point function for the propagator by path integral method. Okay. So I'm going to compute basically the object that I wrote here. But for simplicity, I'm going to compute it in Euclidean framework, so in Euclidean space-time, and then I'm going to recover it in real time, so in Minkowski space-time, by doing this trick of Wick rotation. So first step, compute it in Euclidean framework space time. Okay, so I have my Euclidean space-time, and so I am considering my Euclidean space-time here, This is RD. And I have two points, let's call it x1 and x2. And I'm interested in computing the vacuum expectation value, so the matrix element 0, 0 of phi of x1, phi of x2. Okay. And, well, something that was so obvious for me that I omitted to mention it, but it's important. Remember, yesterday when we discussed how we formulate operators in the path integral formulation, in quantum mechanics there was a correspondence principle between the random variables you integrate over in the path integral formalism and the quantum operators. So I expect that to the field operator that I'm going to denote capital phi of x in canonical formalism. The field operator, which is constructed by an adequate, linear combination of creation and annihilation operator of the modes of the field, should correspond just the random variables phi of x, which is that we integrate over in the functional integral. So I want to compute this object, so the expectation value of the random variable phi at point x1 and the random variable phi at point x2 in the functional integral formalism that I just described here. And I want to check whether this correspondence principle still holds by checking whether I recover the result of canonical quantization. I want to check whether this object is going to coincide with this one. Okay. Now, this is very easy to compute in the functional integral or path integral formalism, because this is just given by this kind of object. Replace A by the product of phi of x1 and phi of x2. So, in the path integral formalism, what is this? This is just the integral over d phi, and I'm using the Euclidean field integral of the action exponential of -1 over h bar, the Euclidean action of the field configuration phi, times phi of x1 and phi of x2, divided by integral the partition function, the phi. Okay, so that's the rule of the game. Okay, and these are just Gaussian integrals, because for the free field, the action is quadratic in the field. So, let me use this. Sorry, that's one. We don't need that anymore. And then, I'm going to rewrite this. So, this is black 5. And this one. because this is a Gaussian integral because the Euclidean action is just integral over d dx of 1/2 of d mu phi squared plus m squared over 2 phi squared. And we can rewrite this if we remember that, for instance, we start from a space-time which is periodic in the Euclidean time direction. Let's assume that it's also periodic in the space direction in order to have a finite space and finite time. And then we take the limit when the period in time direction becomes infinite and the period in the space direction becomes infinite. But as long as it's finite, we can make partial integration and then take the limit. So we can rewrite this as, by just partial integration, as integral of x 1/2 of phi of x times the operator minus the Laplacian plus m squared and phi of x, where this is the Laplace operator with respect to x. So this is the Laplace operator. Delta is just sum from mu equals 0 to d minus 1 over d dx mu squared. So this object is a positive definite differential operator. Okay. So we have to compute the expectation value of a random variable that obeys to Gaussian statistics. So the rules of Gaussian integration that you have stated, rules of Gaussian integration is that the expectation value of two random variables, here it's phi of x1 and phi of x2, that's the expectation value of Gaussian, of product of random variables. So that's what is called the variance, the cumulant. It's given by the variance of this quadratic form. So this is given by the matrix element between x1 and x2 of the operator which is the inverse of the quadratic form. This is a matrix element of the inverse of minus delta plus m squared, which is a partial differential operator. Okay. So let me call this object the Green's function g of x1 and x2. And it's going to be the Euclidean Green function. I'm working the Euclidean theory. Okay. So what is this object? It's something that you have, I think, already met in QFT1 and in statistical mechanics. It's the inverse of this operator. So it means that this function g, when you apply the operator, you get the identity operator. But what does this mean? It means that minus delta plus m squared with respect to the variable x1 applied to g of x1 and x2 is a kernel of the operator identity. So it's a delta function of x1 minus x2. Dirac delta function in d dimension. Okay? So it's just the solution of this Klein-Gordon equation with the source term x1. So this is the definition of the Green function in mathematics. Okay. And of course, so it's an object which is very well known. And the simplest way to compute it, oh, something important. I forgot the h bar, which is in the action, in the path integral. Yeah. So this is, there is an h bar here. So this is h bar times the green function, where the green function is defined in this way. Okay. Okay. So there are many standard ways to write this. For instance, well, of course, this equation has some many solutions because it's a second order differential equation. So you can add to a particular solution of this equation any linear combination of plane waves. But plane waves are exponential in this case because it's an elliptic operator. This is an elliptic operator in RD. We are in Euclidean spacetime, not in Minkowski spacetime, where this would be a hyperbolic operator. Okay. But of course, then, if you think about it, you have to solve this equation in periodic space and periodic time and take the boundary condition, which means that this solution, this one shouldn't grow too fast. It shouldn't grow exponentially at infinity. And this picks up the unique solution. And the unique solution is the following. So, well, you have different way. You can, well, of course, the simplest way is to use the Fourier transform. So you use the fact that it should be invariant by translation. So GE of x1 minus x2 is a function of x1 minus x2. Then, if you assume that this is an object that doesn't grow at infinity too fast, you can define from G of x, Ge of x, you can go to Fourier transform G hat E of k. Fourier transform. And of course, the Fourier transform of this equation is the Fourier transform of minus the Laplacian is k squared. So k is an operator is a vector with d momentum, conjugate momentum, conjugate. X. Okay, and this equation becomes, of course, k squared plus n squared of g hat e of k equals 1, the identity, where k squared is just sum from u equals 0 to d minus 1 of q u squared. That's the norm squared of the operator. And therefore, g of e of k, the Fourier transform is just Lorentzian, k squared plus m squared. Okay, and therefore, GE of x is its inverse Fourier transform, so it's integral d of k over 2 pi to the power d e I k dot x divided by k squared plus m squared, which is an object you have met in the statistical mechanics course. Okay. Well, in fact, you can perform the integral, or you can solve this equation explicitly by going to radial coordinates. So in fact, you can also show that this is given by some Bessel function. So it's 1 over 2 pi times the norm of the vector x divided by the mass parameter to the power 2 minus the dimension of space divided by 2 times the Bessel function is index 2 minus d divided 2 of the norm of x times m. So that's the explicit formula where k nu is modified Bessel function that we find in the table. Okay. Okay, you have 10 minutes left, or 15. I started a bit late. So, let us...
I got lost. So,
Pardon?
there we started with the Euclidean action, right?
Yes.
And we put the Laplace
Yes.
operator there, and then we integrate, and we still have the Euclidean Laplace operator, and then we went to the Lorentzian.
No. This is still Euclidean. Everywhere this is Euclidean. I have not yet.
Just Lorentz.
That's something. It's the formula for the Euclidean propagator.
Okay.
Here I've just started by this equation where this is a Laplacian in Euclidean space. So it's not the Klein-Gordon operator. It's just the Laplace operator,
Okay.
whose Fourier transform is k squared, and of course k squared is positive because this is the sum of the square of the components. So this is Euclidean propagator. So this is the Euclidean propagator. Okay. Sorry, I should have stressed that. Okay. So now I'm going to discuss, that's the last step, the second step. Okay. How do we go back to the Minkowski space-time? Well, we just have to apply the rule that we discussed yesterday. How do we get the propagator in Minkowski space-time? Well, again, we just have to apply the rule that we have seen yesterday for quantum mechanics. We just have to perform a Wick rotation to go back from the Euclidean coordinates, which was tau and x, by writing that tau is now minus I times the real time, and to go to x, which is, I'm sorry, so this is x is a vector in Euclidean space-time, so its first component is Euclidean time, and the next one are the Euclidean space coordinate, to go to a vector coordinate in Minkowski space-time, so space-like vector, whose component has physical time and x. So this is time and physical time, and this is Euclidean time. Okay. So in other words, think now about our Euclidean space-time as, so I'm going to draw the Euclidean space-time as a space-time, you know, where the time, so this is Euclidean space-time tau, and this is space direction. So this is a plane which is seen like that, and you make a Vic rotation in the time complex coordinate to end up with a plane which is like that. So I'm going from this to this. So this is my Minkowski, and this is my Euclidean space-time. So I rotate time, but I keep x fixed. Okay? Okay. So now, well, it's easy to see what we get. For instance, if we start from this coordinate. So let me rewrite this as, let me start from this formula. So GE of x, GE of x, and so x, remember, x is tau and x. And this is an integral of a k, but k is a momentum, so I'm going to write in Euclidean spacetime k to be an Euclidean momentum. So it's going to be k0 and k. So k0 is the first component of the conjugate momentum to Euclidean spacetime. So I call it k0, and the last one are the conjugate momenta to the coordinate spacetime. Okay? So g of tau x is integral of d over dk0 over dk over d minus 1 divided by 2 pi to the power d, and then I get exponential of I times k0 times tau plus k times x divided by k0 squared plus k squared plus m squared. Okay, so I've just separated the first Euclidean time component of the position and of the conjugate momenta from the space component of the Euclidean position and the Euclidean momenta. Okay. And now I want to perform this Vic rotation. So in my time variable, I want to make a Vic rotation. So I want to make, so here is my tau variable. And I can, well, let me write it like that. So this is tau. And I want to start from a tau which is real and make it imaginary, but with an I tau. So I want to go from tau to t. So I make a rotation by an angle plus pi over 2. This is a Vic rotation. Okay? I want to make this change of variable here and see what's happened to this function. And this function, you can see easily from that it is analytic in tau, the tau variable. It's analytic in tau close to the real axis, at least close to the real axis in tau. Okay. So of course I can make this change variable, change tau into I t. But then of course this phase gets a real part, which, for instance, if k naught, so I get minus k naught t, And if k naught is positive and t is positive, this is growing. So when I make this change of variable over tau, I must rotate the k0 integration contour accordingly in order to keep a phase here so that this integral makes sense. But it's allowed to rotate the contour of integration because I am integrating over k0. So let me just now draw the k0 plane. So this is the time plane, and this is the conjugate momentum plane for the time coordinate. So when tau is here, somewhere here, I'm integrating over a contour of integration for real k naught. You see? So this is my contour of integration over k naught. But when I rotate, make a Vic rotation of tau, I must change the contour of integration over k naught in order for this phase to stay real. So when I go, I choose a k naught, which is somewhere here. It's clear that I must choose a path of integration, which is something like that. You see? And when I end up here, my contour of integration is something like that. Okay. And so the natural choice is to choose that if I change during a Vic rotation, so if I perform a Vic rotation, and I write that tau is I t, I must change my variable k naught into k naught equal minus I omega, where I have a contour integration omega, which goes from minus infinity to plus infinity. So omega is minus the imaginary part of k naught, while t is the imaginary part of tau. You see? So this is Vic rotation. The Vic rotation, in fact, in the formula, is to make simultaneously a Vic rotation on Euclidean time and a Vic rotation in the opposite direction, in anti-Vic rotation, on the conjugate momentum. Okay? And then, of course, what we get is that when we make this change of variable, but we get that this becomes g of t and x, which is, so I change k naught is into minus I omega. So I change integral from minus infinity to plus infinity of d omega over 2 pi, and I have a factor minus I. Okay. I have this becomes exponential of I times, so k naught becomes omega, tau becomes t, k is unchanged and x is unchanged, it's not a post variable, and here I get, of course, minus k squared minus omega squared plus the space momentum squared k naught plus m squared. Yes?
Should there be a minus sign in the exponential in front of the minus omega, in front of the omega t?
No, because I choose this
Okay.
and this. So they compensate. Okay, so.
Sorry, are the d minus one dimensional integral is still there as well?
I don't change them.
It's still there.
I don't make a Wick rotation on k and x, and k vector and x. Those are the space. Here I don't touch space.
Yeah.
Okay, so now we are almost done. You just have to remember that now in the omega and k variable, this has a pole. There is a pole at omega squared equal k squared plus m squared. Okay. Which reflects the fact that in the original integral, here, where was it? This has a pole at k naught squared equal minus k squared plus m squared, which is positive. So in fact, there is a pole here at k naught equal plus I square root of k squared plus m squared, and here another pole at k squared equal minus I square root of k squared plus m squared. These are the poles. Okay, you see? So we need the prescription to deal with the pole in this integral. But we know the prescription because we have a pole, we start from a contour of integration like that, and we rotate it like that. So we end up with going around the pole like this and this. Okay. So in other words, in the omega plane, we have a pole here at plus square root of k squared plus m squared. We have a pole here at minus square root of k squared plus m squared. And my contour of integration is, remember, I'm just rotating this like that. So my contour integration is like that. Okay. So this contour corresponds to the Feynman propagator. So it corresponds to add to here a prescription minus I epsilon plus. See. You can check. Usually this is written as omega squared minus k squared minus m squared plus I epsilon plus, which means that here we have a plus I and not a minus I. So g of t, so the Wick rotated Euclidean propagator is the Feynman propagator. Let me state here to be clear. Wick rotated, well, no, here you are. Wick rotated propagator equal Feynman propagator. Which means that through the Wick rotation, we recover the expectation value in the vacuum state, in the vacuum of the field theory, of the time-bordered product of the two field operators, which are now located at x1 and x2 in Minkowski spacetime. Because now x1 is some t1 x1. So now we have Minkowski spacetime, and Minkowski spacetime, this is time, this is space, and this is x1 is t1 x1, x2 is t2 x2, and the fact that we get the time-ordered propagator through this rotation means that we take into account the Wick, the causal, the fact that whether x1 and x2 as causally separated or space-like separated and time ordered. So causality, so we recover the causal structure. Of my quantum field theory that was obtained by the canonical quantization. Okay. Well, I'm already a bit late. So let's end today's lecture.